In this question we're going to look at the values of magnetic field for a search coil as it moves along the x-axis placed next to an electromagnet. You can see the graph there following some kind of 1 over r squared it looks like, which is kind of what you'd expect. Part 4.1 is actually pretty straightforward. You're just asked to find the value of the flux linkage at a particular distance. We're then told that the search coil is moved at constant speed along the x-axis away from the electromagnet. Now that must be very hard to do, nevertheless they find a way to do it. And you can probably see that in 4.2 that the size of the EMF induced is going to drop off because B is changing, therefore the rate of change of flux, which is what produces the EMF, is going to decrease. At 4.3, now this is a difficult one. So on to the hard bit then. Our coil passes through a distance of 0.1 metres and carries on with x increasing. And we're asked to find out if once it's got past 0.1 metres, the voltage can exceed 5 millivolts. Now we know that at 0.1 metres, the strength of B is greater than it is at any distance out beyond 0.1 metres. Therefore, if we've got 5 millivolts, or less than 5 millivolts I should say, at x equals 0.1, it's going to be less for any other distance. So really what we have to do is find the EMF at 0.5 volts. As I've worked on this question with students over the last week or so, I've noticed that mostly their approach is to recall the formula for EMF induced, which is a good start, but then to draw a red line, something like the one I've drawn, at the distance of 0.1, so that they can read off the value of B. But there's also a couple of issues with this, because firstly our formula's got delta phi in it, but that's not so bad because we know that phi is equal to BA, so maybe we can work with that. But more importantly, we know that the EMF induced is actually proportional to the rate of change, and at this point students are using a fixed value, so they're barking up the wrong tree. So the next way to look at this is to think, well, I've got to get a rate of change in there, and you know, that's normally a gradient, isn't it? But then this gets confusing because what actually is this gradient? So if you think about delta B over delta X, how is that going to relate to our formula for n delta phi over delta T? Well, the big link into this question is to remember that velocity, of course, it is distance over time, which you just know because you've done it so many times. That means, of course, then that distance is going to be equal to velocity times time, velocity times time. So taking it as a gradient, this is going to mean that the change in the distance, which for us is x, so delta x equals the velocity delta t, which therefore means that delta t is going to be equal to delta x over v. And now we have a way into our formula up here. So our next task then is to substitute out delta t, so let's just get rid of it. Goodbye delta t, and then we're going to put in delta x over v. Now algebra fans, which of course is all of you, will know now that that EMF is going to be minus n times v delta phi over delta x. Last step then, we're going to substitute in for delta phi there. We're going to write BA. So that becomes BA, and we know A is a constant, so we can take that outside of our expression, so that gives us that EMF is equal to negative of n v velocity A delta B over delta x, and of course this is the gradient of our red line. Now I've run out of time because I have a lesson coming up in 2 minutes and I need to rush, so I'm going to leave you to put in the numbers. Just take the gradient of this graph, being careful to remember, of course, it's negative because it's going downhill, which means the negative from the red line and the negative from the formula cancel out, and you will get a value that is a bit less than 5 millivolts. Therefore, we cannot exceed that value as x moves outwards.